All right, let's talk a little bit about the ionic bonding. We know that the ions are made. Things like aluminum are going to lose 3 electrons and make a +3 ion. Oxygen is going to gain 2 electrons and make a -2 ion in order to satisfy the octet rule. Those electrons that the aluminum wants to lose are the same electrons that the oxygen wants to gain. These two are going through this process together. The metals and the nonmetals have to get together in order to do that exchange. So the metal's going to lose and the nonmetal's going to take. The metal becomes positive, the nonmetal becomes negative, and these two ions are then attracted to each other, forming what's called an ionic bond. It's defined as the attraction between positive and negative ions. Again, once something like aluminum becomes positive and the chlorine or the oxygen takes the electrons and becomes negative, we're going to end up with positive and negative ions. And those positive and negative ions are going to be attracted to each other. They're going to stick together like a magnet on a refrigerator and make an ionic bond. The result of which is going to be an ionic compound. Ionic bonding produces ionic compounds, and ionic compounds have a specific set of characteristics. They tend to be hard. They tend to be solids at room temperature. They tend to have high melting and boiling points. They tend to conduct electricity in a liquid phase. The solid won't do it. The ions have to be able to move around. That's either done when it's melted or dissolved in water. In the liquid, or we can say aqueous phase. Aqueous just meaning dissolved in water. Think rock salt, very hard substance. If you try to chew on it and bust your teeth, it's a solid at room temperature, has very high melting and boiling point, and conducts electricity when you dissolve it in water. These are all the properties of ionic compounds. It's important to note these are not usually the same as the elements that make them up. The elements that make them up can have very different characteristics. Table salt's a great example. Sodium is a soft silver metal with a relatively low melting point, just over 200 degrees. Whereas chlorine is a green gas. It's already melted, in fact boiled at room temperature. When you combine them together and make table salt, it's a very different substance. It's a much harder substance with much higher melting and boiling points. The melting point of salt being over 1800 degrees Fahrenheit. Very high temperatures involved to melt it. They behave differently because they're not the same as the elements that make them up. Once they make this ionic bond, once they've joined together to make this ionic compound, they have truly become something different. We talked about using Lewis structures in order to model this bonding process. Lewis structures show the valence electrons in an atom. So we talk about aluminum, the example I used in the last video. Aluminum's in group 3A. It has 3 valence electrons. If we want to show those 3 valence electrons, we'll draw its Lewis structure. Now, there are rules for this, and we really didn't get into the rules about maximizing the number of single dots, minimizing the pairs, etc., etc. What I said was, when you do these Lewis structures, start on one of the 4 sides. And you can either start at the top, the right, the bottom, or the left. Put a single dot in at a time until all your dots are accounted for. This will take care of all the rules. This will make sure everything gets done correctly. So again, aluminum has 3 valence electrons. So I would draw them in like so, as 3 singles. And that is very important. Again, there are rules that go to this. You have to minimize the number of pairs. You got to maximize the number of singles. If you just do what I told you to do, one dot at a time, working your way around the four sides clockwise, one dot at a time, you won't double them up until you have 5 dots. That'll work, because that's going to minimize the number of pairs for us, automatically going to maximize the number of singles. We can see this with oxygen, the other example that I did in the other video. Oxygen is a nonmetal with 6 valence electrons, in group 6A. I have 6 dots to put around it because of the 6 valence electrons. Again, top, right, bottom, left, those are my 4 sides. I do 1 dot at a time on each side, working clockwise. So 1, 2, 3, 4. And as I said, we don't start doubling up till we get to 5. So the 5th dot makes our first pair. The 6th dot will make our second. And what we've done here is we've minimized the number of pairs, maximized the number of singles by just working our way around that oxygen 1 dot at a time until we finally have all 6 done. Now these Lewis structures tell us a little bit about these atoms. Again, we look at aluminum as a metal. It's to the left of the metalloids where metals are supposed to be. And like all other metals, it has to lose its valence electrons to become stable. And we see that it's got 3 dots here. We can see that it's got 3 valence electrons. We know that aluminum has to lose 3 electrons in order to attain stability. For a metal, its Lewis structure does not become stable until it's lost all those dots. We look at oxygen and we see these 2 singles here. These 2 singles imply we've got space for 2 more electrons. We can pair those up, indicating that our oxygen needs to gain 2 electrons in order to attain stability. We have to find a partner for those 2 pairs. The actual bonding process here is going to involve more than 1 atom of each of these 2 elements. It's going to take more than just 1 aluminum. It's going to take more than 1 just oxygen to get this done, because when we look at what we're dealing with, things don't add up. If aluminum needed to lose 2 and oxygen needed to gain 2, this would be cut and dry, simple, ready to go, no issues. Or if aluminum needed to lose 3 but oxygen needed to gain 1, again, that's pretty easy to figure out what's going to happen there. We need 3 oxygens to get it done, but that's not the case. We have something needs to lose 2, something needs to gain 3. So we're going to draw this out and we're going to model the bonding to figure out what happens here. I start by drawing in my aluminum atom with its 3 valence electrons. And I draw in 1 oxygen atom with its 6. And I do what I can do. Move 2 electrons over to the oxygen, like so. I can't move this 3rd one over because at this point I filled the 2 spaces that I had. We can only gain 2. I'd have 2, 4, 6, 8 valence electrons around the oxygen at this point. It can't take any more. But here's poor aluminum with another electron left to get rid of. We can't leave it that way because that would actually make the aluminum a lot less stable than what it was to begin with. Whenever we have more electrons and not enough spaces, the only logical thing to do is bring in more spaces. Draw another oxygen atom. And again, do what you can do. I can move 1 electron over. Satisfies the aluminum's needs, but now we have an oxygen atom that's unstable. And again, worse off than what it was before. It has another room to fill. It's got 1 more spot for electrons, and we need to give it electrons. And anytime that's the case, you have more room to fill and not enough electrons to do it, you've got to add another metal. We transfer that electron over, and poor aluminum's got extra electrons it's got to dump off. It's got to get rid of. Again, we can't leave it like this because that would make the aluminum worse than what it already is. And again, anytime that happens, you've got more electrons to get rid of, you're going to need more nonmetal atoms. Bring another oxygen, transfer the electrons, and again, take a look. All of our metals have dumped all their electrons. Both aluminum atoms have gotten rid of all three. Our oxygen atoms all would have 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. All of our oxygens will have the 8 that they need to become stable. Everything satisfied. Octet rule accomplished. That is exactly what would happen in our ionic bonding scenario. It would take 2 aluminums and 3 oxygen atoms to get everybody happy. Now what this does is establish a ratio. It allows us to write what's called an empirical formula. The empirical formula tells us the ratio of the elements. The formulas have to be written in specific ways. First of all, when you write the formula, you have to write the metal first. So metal, nonmetal. When you write subscripts on the formulas, they indicate how many atoms of that element you have. They always go after the symbol, and you never write down the number 1. So if there's 1 of anything, just leave the subscripts off. It's always assumed that if there's no subscript, there's just 1 of them. And then finally, you have to reduce where you can. Now this won't be an issue when it comes to Lewis structures. It'll only happen with a shortcut. But you have to check those subscripts. If they can be divided by any number to be reduced, you have to do that. You have to write them in the lowest terms. Reason for that, empirical formulas are ratios. And ratios are always written in the lowest form. Basically, with the Lewis structures, we just write what we see. We start with the metal, the aluminum. There are 2 of them, so we write Al2. Then we move to the nonmetal. There are 3 of them, so we write O3. Al2O3 would be the empirical formula for this combination. Again, what it's saying is it takes 2 aluminums for every 3 oxygens to attain complete stability, to make sure every atom satisfies the octet rule. And again, this type of formula is called an empirical formula. It is a ratio. It's the ratio of aluminum to oxygen in this case. Now, if you had to write all your ionic formulas this way, it would take forever to write ionic formulas. You'd be drawing Lewis structures and arrows all over the place. If I gave you a set of 20 or 30 of these things to do, to write formulas for, it would take you a good bit of time. Getting all the Lewis structures straight, getting all the modeling done, figuring out how many atoms it takes, that's just too much. So there is a shortcut. And those shortcuts involve oxidation numbers. Basically, there are some very predictable groups on the periodic table. Group 1A, 2A, 3A, 5A, 6A, and 7A. Those are the most predictable groups in the periodic table. The metals in 1A form +1 ions. The metals in 2A form +2 ions. The metals in 3A form +3 ions. 5A form -3 ions. 6A -2, 7A -1. And this does relate directly back to the ion stuff that we learned earlier. For example, beryllium. Beryllium is in group 2A. What that means is beryllium has 2 valence electrons. Beryllium is a metal, which means it has to lose those 2 valence electrons to become stable. In both the neutral atom and the ion, you find 4 protons. Beryllium is atomic number 4, has 4 protons. In the neutral atom, you'd have 4 electrons. But we have to lose 2. So there are only 2 remaining. When we go to look at the charge here, we end up with +4 plus -2. 4 from the protons, 2 from the electrons. And protons are positive, electrons are negative. The net charge in this case is +2. And that is the oxidation number we see for the group that it's in. everything in group 2A will do this exact same thing. So we say group 2A has an oxidation number of +2, or all the elements in group 2A will form a +2 ion. It's important to note that these negative ones apply to nonmetals, while these positive ones apply to metals. Not so important with 1A through 3A because those groups are almost entirely composed of metals. But when you get into 5, 6, and 7A, there's a mix of elements there. They're called the mixed groups. We have metals and nonmetals in all of them. We have metalloids in others. So again, we got this mix of elements here. It's important to recognize that these oxidation numbers apply only to the nonmetals in those groups. What we're going to do to write the formula using the shortcut is called the Crisscross Method. We'll look up the oxidation numbers. Check and make sure we have one that's positive, one that's negative. Make sure we know which one's positive, because by rule the metal has to go first. The metal will be the one with the positive oxidation number, so it's important to make a note of which one's positive. Look up the oxidation numbers, recognize which one's positive, which one's negative. Swap them. The metal's oxidation number is going to become the subscript on the nonmetal. The nonmetal's oxidation number becomes a subscript on the metal. We're going to have to reduce this time. Like I said, in Lewis structures, when you're using the Lewis structures to figure out the formulas, that's not an issue. When you do the shortcut, it is. You have to make sure they're reduced. Odds are it's going to be two oxidation numbers that cancel out, the +2 and a -2. You'd have a 2-to-2 ratio. You reduce that to 1-to-1. Again, think of it as those charges canceling out. If you have a +3 and a -3, you swap them, you'd end up with 3 on both of them, and it's a 3-to-3 ratio. That reduces to 1-to-1. Again, it's more an act of the charges canceling out. And if they cancel out, you have to do that. You have to reduce them completely to 1s and not write anything at all. And again, remember, when you write it, put the metal first. So we pick two elements, just down at random here, and we're going to do potassium and oxygen. Figure out what the formula for that combination is going to be. Again, we got to know the oxidation numbers for each one. Potassium is in 1A on the periodic table. Here's something I was going to tell you. And oxygen is in 6A. 1A's oxidation number is +1. 6A's is -2. And again, the positive and negative part, that's not all that important. We just have to make sure we have a positive and a negative. If we're doing ionic bonding and they both end up being negative, we know we did something wrong. They both end up positive. We know we did something wrong. Something needs to be positive, something needs to be negative. And we also have to make a mental note of which one's positive. The potassium's positive, so it has to go first in our final formula. So again, I just want to make a note, this was the positive one. The 1's going to go here, the 2's going to go here. We're going to swap the numbers, so it's called the crisscross method. We're ready to write the formula. K2 is good, but O1 is not. We cannot write down the 1, so we're just going to put O there. Leave the 1 off of it, you're not allowed to write it. This can't be reduced because it's a 2-to-1 ratio. 2-to-1 ratios are already in the lowest term. Nothing you can divide those by to make it any smaller. Let's do sulfur and calcium. And again, since you don't have a periodic table, there's not one up on the board here. Sulfur is 6A and calcium is 2A. And again, 6A has a -2 oxidation number and 2A has a +2. I have a positive and negative like I'm supposed to have, so I know I've looked them up correctly. Again, if they were both positive or both negative, I know I made a mistake. I know that one's the positive one, so when I do write my final formula, I am going to have to put the calcium first. 'Cause the calcium is the positive one. I know that one's the positive one, so when I do write my final formula, I am going to have to put the calcium first. I know that one's the positive one, so when I do write my final formula, I am going to have to put the calcium first. 'Cause the calcium is the positive one, so when I do write my final formula, I am going to have to put the calcium first. When I swap the numbers, I end up with 2 on each. 2 to 2 ratio is not in its lowest terms. Your math teacher wouldn't let you write that down. I won't let you write that down. Both of these can be divided by 2 and reduced to 1s. And again, 1s don't get written down. So we write CAS as our final formula. To do this, obviously you have to work with predictable substances, those that have easily obtainable oxidation numbers. That means no metals out of the B groups. If I were to ask you to do something at this point with a metal out of the B groups, I would have to tell you what the charge is. There's a lot more reducing that takes place in the B groups. I will warn you of that. There can be the potential for +4s and +6s and things like that there. But again, I will tell you what the charge is by writing it on the symbol. So if I wanted to combine together manganese and oxygen, I'm going to tell you what the charge on manganese is because you can't look it up. All you have to look up is that oxygen, which again is in 6A and is a -2. 4 is going to come over here, 2 is going to come over here. Again, these can be reduced. There's a lot more reducing to do with B groups. Both of these can be divided by 2, leaving us with a 1 to 2 ratio. Again, positive first. So metal first. Don't write down the number 1.